Hi everyone and welcome back to my channel AM Economist. So today we are going to cover our final topic in time series analysis where I'll discuss the tests that are required to test the stationarity of a time series data. So we have already covered the important time series processes and we have also seen how to estimate them. So now it's time for us to understand how we can test for stationarity. So previously I have mentioned why stationarity is at all important in case of time series analysis. If you haven't watched that video, I'll give the link in the description. You can check that out. And now let us move to the tests of time series. So there are two primarily used tests that we frequently use. The first is the Dickey Fuller test, which is also known as DF test. And the second one is also known as the Augmented Dickey Fuller test or the ADF test, right? So there are two basic tests that we will cover in this video. So let's start with the Dickey Fuller test or the DF test. So it says Dickey Fuller is a statistical test that is used to check stationarity in the time series. And this is a type of unit root test. So please understand, this is a very important point. What is a unit root? I'll be covering that as well. So this is a type of unit root test through which we find if the time series is having any unit root. Now this paragraph explains what is a unit root. Unit root is a feature of time series that indicates if there is any stochastic trend in the time series that drives away its value from the mean value. So I have told you earlier, suppose that expectation of a time series process is like this, A into T, where A is greater than 0. So what happens is that as the value of T changes, suppose it increases or it decreases, the expectation also changes. Expectation follows a trend. Either it's an upward trend or it's a downward trend. And when this kind of trend arises in a time series data, what happens is that it drives the time series away from the mean value. It drives the time series away from the mean value, which basically means the time series becomes non-stationary, right? So I will say that I have explained this concept in details. So please check the video out if you, don't understand what I'm saying right now. So what happens? That unit root is a feature in the time series that indicates that if there is any stochastic trend in the time series or not. And if this stochastic trend exists, what happens is that the time series becomes non-stationary, as simple as that. So that is what written here, that presence of unit root makes a time series non-stationary. And as a result, it leads to difficulties in deriving statistical inferences and future predictions. So stationarity is a very crucial, concept in case of time series. Before proceeding with the statistical inferences and, deriving predictions and forecasts, it is mandatory that our time series data is converted into a stationary time series. If it is stationary from the beginning, then there is no issues at all. But if it is non-stationary, then you have to convert it into stationary. And in order to convert that, first you need to know what is the test of stationarity. How do you check that the time series is stationary or not? For that, the first test that we use is the Dickey Fuller test. So let us now straight dive into what is a Dickey Fuller test, and I'll take you through the steps how you perform that. So what is a Dickey Fuller test? Dickey Fuller test assumes an AR1 type of type series model. This is a very crucial point, that in case of Dickey Fuller, we assume that the time series data, suppose YT, and T is from suppose 0, 1, 2 up to N. So this is the time series data that is available to you. Now Dickey Fuller test assumes that this time series data follows an AR1 process. So you have picked the time series data up from the AR1 process. Now how does this AR1 process looks like? I have told you multiple times, this is the general structure of this AR1 process. So it can be represented mathematically as this: yt is alpha plus phi yt minus 1 plus epsilon t, where epsilon t follows white noise. Now what is your hypothesis? If you have seen my AR1 video, I have told you whenever mod phi is less than 1, the AR1 process is stationary. So see, I have defined the hypothesis in that way only. Everything depends upon this slope parameter phi. So if the value of phi is equals to 1, it means that there is a presence of unit root in the process. And I have just mentioned here, if there is unit root in the time series process, it will make this time series non-stationary. So your null hypothesis, this is the null hypothesis H naught. It says if phi is equals to 1, right? Null hypothesis assumes that the process is non-stationary, that is, it has a unit root. And the alternative hypothesis says it is phi is less than 1, which means that process is stationary and it does not have a unit root. So I hope up till this much this is clear, that whenever we know that for AR1 process, whenever mod phi is less than 1 or phi lies between -1 to +1, the process is stationary. So that is captured by this alternative hypothesis. Alternative says the process is stationary, whereas null hypothesis says the process is non-stationary. Now, what do we need for testing this hypothesis? We need a test statistic. What is test statistic? Test statistic will depend on the value of phi only, the estimated value of phi. T will be, depending upon phi cap. Phi cap is the basically the OLS estimator of phi. So from here, I have also mentioned that, also derived in details how do you find out this estimated value of phi in some of my video. So I hope you have seen that. So you know how to find out the estimation. Estimation was our previous topic, so I have covered in details. How do you find this phi cap? So phi cap. So how do you build up this test statistic? So first write the estimated value of phi that you get from any method. It can be from OLS method, it can be from OLS method, it can be using method of movements, or any which ways you can find that out, minus the phi value in H naught. So what is the phi value in H naught? Phi value in H naught is 1. This upon the standard error of phi cap OLS, right? This is the general structure in, we, write every test statistic in the similar way. First, we write the estimated value of the estimator that we have obtained using some method, minus the parameter value that is defined in the null hypothesis. This is important, that parameter value that you have defined in the null hypothesis. And then in the denominator, you write the standard error of this estimator, OLS estimator. So here in the next step, I have just replaced this phi H naught to be 1, and the rest of the things are same. And now under H naught, since we have, used the value 1, so we are assuming that a test statistic is derived assuming H naught is true. So under H naught, this is the sign of under. Under H naught, this will follow Dickey Fuller distribution. So Dickey Fuller means that it is the same like you have used in the T distribution or Z distribution. If you know the concept of hypothesis testing, I'm sure you know. So in the statistic books, you find the table for T statistic values and the Z values. So Z table and T table are available to you. But this is the similar thing. DF is also a table that you find in the statistics books. And from that, you have to compare this calculated value and the critical value. So here from this step, you find the calculated value of T cap, and from the table, you find the critical value. Suppose this is T alpha. This is the critical value, and the conclusion can be derived comparing the values of this T phi cap and T alpha. That is the calculated value of T and the critical value of T. This is usual process how you perform the hypothesis testing. So only difference is in the test statistic. The rest of the things are same, and it basically follows the Dickey Fuller distribution, right? It is the same as T distribution and Z distribution. They are separate distributions, and this is also separate distribution. And the table is also given in your statistics books. So this is how you perform this test. But there is another aspect that I wanted to cover, that you can rewrite this into a better way. So this is the AR1 process that we started with. Now, if you subtract this yt minus 1 on both sides, what happens is that you get the lag value. This is also something that I have covered previously. What is lag? This is lag of degree 1. So lag of degree 1 is basically yt minus 1. Lag of degree 2 will be y, uh, basically delta yt. So basically delta of yt minus 1. So in this way it follows. So here you have yt minus 1. So it will be delta yt, and the rest of the things, from the rest of the things, if you take yt minus 1 common, you have phi minus 1. And in the next step, phi minus 1 is assumed to be some delta, some parameter delta. Now, what you can do, you can define your hypothesis in terms of delta as well. So in the first case, what we have done, we have taken the AR1 process as it is, and we have just compared the slope parameter, and we have defined hypothesis based on that. But here what you can do, you can convert the AR1 process into the lag representation. This is the lag representation of AR1 process, right? Now what you can do is that you can again take the slope parameter is delta here, and define your hypothesis in this way. If delta is 0, now delta 0 means what? Delta is nothing but phi minus 1. So basically means phi minus 1 is 0 or phi is equals to 1. So this is the same thing that we have done earlier. If you see, this is phi equals to 1. That can be written as delta equals to 0, which means that the process is non-stationary and it has got a unit root, right? That is what I have written here. But see, when delta equals to 0, when suppose this variable is 0, so what happens is that this term entirely becomes 0. If null hypothesis is true, this term is entirely 0. So delta yt becomes what? Delta yt is alpha plus epsilon, right? And this is always stationary because this is epsilon. Epsilon follows white noise process and alpha is just a parameter. So delta yt is stationary, but the process yt is non-stationary. I hope this is clear. It may sound little confusing, but this is, I hope you got the logic. That when you put delta 0, what happens is that delta yt becomes alpha plus epsilon t, which is stationary. But the original process yt, this becomes non-stationary. Why this is non-stationary? Because I have mentioned that phi is equals to 1. Delta equals to 0 means in the original AR1 process, which is not the lagged version, this is the original process. Here, if you put phi equals to 1, it becomes a random walk model, and random walk model is always non-stationary because it has a unit root. And the alternative hypothesis here will be delta less than 1. And it is also the same thing, phi minus 1 is less than 0. So phi is less than 1. And again, it is the same thing here. Alternative is phi is less than 1. Right? So this is the entire thing about Dickey Fuller test. Now, how do you define the test statistic? Again, the same thing. Now, the test statistic will be defined on delta cap. So you have delta cap minus delta value under H naught upon the standard error of delta cap. Again, delta cap can be found out using OLS method. Now replace delta value under H naught. Now this value is 0. See here, the delta value under null hypothesis, it is 0. So this becomes 0. Now, test statistic is always defined in assuming that the null hypothesis is true. So this is something that you need to remember. Okay. So if you put here 0, then it becomes delta cap upon standard error of delta cap, which under H naught follows Dickey Fuller distribution. Again, the same thing. And the rejection criteria, if the test statistic is less than the critical value or the p-value is less than alpha. If the p-value is less than alpha, this is the thumb rule that we reject null hypothesis. Remember this, this is the thumb rule for every hypothesis testing that you do. Whenever the p-value is less than alpha, we always reject the null hypothesis. This is a thumb rule that you must remember. And so if the test statistic is less than the critical value or p-value is less than a p-specified significance level, then what happens is that null hypothesis is rejected, and rejection of null hypothesis means the process is considered to be stationary. This is what I have told you so far. Please refer to this thing again and again if you have any confusion. That null hypothesis assumes that the process has a unit root. It is non-stationary, but the alternative suggests that it is stationary. So if you reject null hypothesis, means that alternative is true. So phi is less than 1, which means that the process is stationary. And that is what this rejection rule says. If p-value is less than alpha or the test statistic is less than some critical value, the null hypothesis is rejected, and this implies that the time series is stationary. Whereas if the test statistic is greater than the critical value, the null hypothesis cannot be rejected, which means that the process is non-stationary. As simple as that. And the critical value is found using the Dickey Fuller table. This is also I have mentioned sometimes back that Dickey Fuller is a separate table that you find similar to T table that we use for T test, and we have a table with critical values for Dickey Fuller test as well. right? So this is all about Dickey Fuller test. I hope you find this useful. Now let us get back to augmented Dickey Fuller test, and we'll also discuss what is the difference between the two. So augmented Dickey Fuller test, which is also called the ADF test, is nothing but an extension of the Dickey Fuller test for more complex models than AR1. So the primary difference between the two tests is that ADF is utilized for larger sized set of time series models, which can be more complicated. So please remember the thumb rule that Dickey Fuller test always assumes an AR1 process, right? This is we have discussed. Now ADF test assumes ARP model or ARP process. That is, Dickey Fuller test assumes that the time series data is following an AR1 process, and ADF test assumes that time series data that we have used in order to estimate the parameters is following an ARP process. This is the primary difference between the two tests. Now we will do the same thing. Firstly, we will write the ARP type of time series model. I have explained in details what is ARP in a separate video. You can refer to that. So yt is written as this: phi1 yt minus 1, phi2 yt minus 2, and this is the general structure of ARP model. Epsilon t follows white noise. So again, what you have to do, you have to find out the lag version of this model. And now this process becomes a little complicated. How do you find out the lag value of this? I have given you the entire thing. You can, pause the video, take a screenshot, and, do it on your own. I have written everything. We'll be coming to that. So firstly, write the lag value. So yt minus 1 is L into yt minus 2 is L square into yt, and it goes on. So if you take this on the left hand side, you have this. Take yt common, you have 1 minus phi 1 L minus phi 2 L square minus phi 3 L cube all the way to pi p L to the power p, which is also called the characteristic polynomial of ARP process, if you remember. Now, what you have to do? You have to do something. You have to define some variables. First variable is rho. What is this rho? Rho is the summation of this coefficients. Here you have phi 1, here you have phi 2, here you have phi 3, up to phi p. So if you take the sum of this, suppose we define this to be rho. Rho is summation I from 1 to p phi n. And you have another variable delta j, which is written as this: minus of phi j plus 1, phi j plus 2, phi p. And j is all the way to this. Again, I will suggest that please pause the video, take a screenshot, and understand what I have done. Okay. Then what do? You write the values of delta j, delta 1, delta 2, delta 3, up to delta p minus 1. These are the values. You can pause and take a screenshot. There is nothing to explain. You have to just understand the process step by step. So I have written everything for you. Now what do you have to do? Okay. Now, suppose we start with this equation. There is no logic in this. If you simplify this, you get back the original characteristic polynomial of ARP process. So 1 minus rho L minus delta 1 L delta 2 L square. So basically what we are trying to do is that we are writing the characteristic equation in terms of the variables that we have defined. That is rho and delta 1, delta 2, and delta p minus 1. So this we have got due to this assumption that rho is this and delta j is this. So if you assume this, you can write this characteristic polynomial in terms of this particular expression, which will come handy in order to find the lagged version of ARP. So simplify that 1 minus this. This is the step that you will get. Again, I will say take a screenshot, do it on your own. There is nothing to explain. Okay. Now, instead of this characteristic polynomial, instead of this, let me get back to this. Yeah. So firstly, we have taken this ARP and converted it into this form. So we are using this form now. In this form, replace the equation that you have got previously. This is the same thing that we have got previously. Now, if you simplify, you get the lagged version of ARP. This is basically the lagged representation. Let me write it here. This is the lagged representation of ARP. I know it is a little complicated. And it is not mandatory for you to, remember everything. Just know the process. I am focusing on the process that if you have this ARP model, you can convert it into a lagged version of it. And once you have this lagged version, only then you can perform the hypothesis testing. So this is the process. You just have to remember the, steps that I have done, nothing else. It's not that mandatory. So this is something that we get. And if you write it in a compact way, this is the final model. So in books, you see that this is the step that is given to you immediately after the ARP process is written. So they basically skip the process in between how you find this lagged version. So finding this lagged version is not that easy. So I hope you understand that you have to follow these steps in order to get to this model. So now I hope you understand that in books, if you see, they directly write this lagged version and students find it very difficult how to derive this thing. So I have derived the entire thing for you. Okay. So you see, we have this version, and then if you take the yt minus 1 on both sides and take common, you get this lagged representation. This is the compact version that we use for our hypothesis testing. So here it is written ADF is the same equation as DF, with only difference being in the addition of differencing term representing larger. So this particular thing is extra. This expression is extra that is used to capture the larger time series, right? Since instead of AR1, we have used ARP, so it is very simple to understand that the process will be a little more complicated than before. So you can compare this with the earlier lag representation. Let me get back. Yeah. So this is the lag representation earlier. Delta yt is alpha plus phi minus 1, yt minus 1 plus epsilon t. So on the right hand side, there is no delta in this representation. But here, if you see on the right hand side as well, you have some lag values. Yes, this term. On the right hand side also, you have some lag values. So it's the same as DF, but the only difference being the addition of differencing terms. Lag means differencing. Differencing term means these lag terms are added representing larger times. And now once you have this, the process is very simple. Again, you have to define the hypothesis testing. Now this rho we have defined to be the summation of phi 1 to phi p. So this rho is equals to 1. The ARP has an unit root and the process is not stationary. So if this is equals to 1, which means this term is gone because 1 minus 1 is 0. This term is gone. You have only this thing. Only the second part is there. And in that case, the process has an unit root and the process is non-stationary. But if this mod rho is less than 1, that is rho is from -1 to +1, if this happens, then the process is stationary. And then you can define the test statistic accordingly. The format is entirely the same. You find out the rho cap using OLS or some method minus the rho value under null hypothesis. Under null hypothesis, what is the value? This is 1. So you can substitute this to be 1 and then find out standard error of rho cap. Under H naught, it will follow EDF, distribution. So again, like Dickey Fuller, you also have augmented Dickey Fuller table in your statistics book. So that will help you comparing with the rejection region. So the test statistic and critical values can be compared in order to find out the rejection region, and the inferences can be drawn accordingly. So I have written test with critical values to conclude the lessons. And that is all you need to know for the Dickey Fuller test and the augmented Dickey Fuller test. I have given you the entire steps. If you have any doubts, any questions anywhere, you can let me know. And if you find this useful, please subscribe to this channel, AN Economist. And later on, when I'll update this playlist, I'll add the forecasting methods in details later on. But as of now, this is the final topic that I have covered in time series analysis. If you like this video, do give me a thumbs up and subscribe to this channel. And after this video, I'll be going into econometrics playlist and I'll cover everything that you need to know in econometrics. So stay tuned for that. I hope you like this video and thank you for your time.